electrophilic aromatic substitution. In electrophilic aromatic substitution, the general picture, and then we'll look at lots of specific examples. That you have a benzene ring plus some electrophile. And how we generate that electrophile is important. And as we go through, we'll deal with lots of different kinds of electrophiles. So we will see lots of reagents that we need to know. And the mechanism of the generation of some of those electrophiles you will need to know, and I'll point those out as we go through. And this reaction then produces the substitution of a hydrogen with the electrophile. And again, this is the core difference between these, what appear to be double bonds in a benzene ring, but it's really a unique functional group, this aromatic ring. And so we see substitution when we preserve the aromatic nucleus because of its enormous stability. So instead of an addition reaction, we get this substitution reaction. Now, the way this reaction occurs is that in the slow step, the benzene acts as the nucleophile reacting with the electrophile. And remember, as I teach this, I'm going to emphasize nucleophiles and electrophiles, because if you can identify those, you can understand the patterns in chemistry. This reacts and produces an intermediate in this intermediate, you see, according to our definition of aromaticity, let me ask, is this intermediate aromatic? Of course, the answer to that is no. And it's the regeneration, so some sort of Lewis base in the reaction, solvent or whatever the counterion is for the electrophile that has a lone pair, then instead of adding to the carbocation, acts as a base, plucks off the proton, the lone pair of electrons swing down to reform the double bond, and we have generated now our substitution reaction product. All right, so the first of the specific reactions that we're going to deal with is bromination. In bromination, we have benzene plus Br2. But if you recall from the beginning lecture in chapter 15, these two just sit and stare at each other. They don't react. So we add a catalyst. In this case, the catalyst is iron tribromide. Now this is a mild Lewis acid that results in the substitution and the production of bromine. Okay, so that's bromination. Now, how does this reaction occur? We're going to look at the mechanisms of these. And for Br2, there's our Lewis dot structure, and of course Br2 is a Lewis base, right? What's the definition of a Lewis base? A lone pair donor. So that lone pair reacts with the Lewis acid. It's a weak interaction, but it produces a strongly polarized bond okay, and this is now partially positive. Not very well. Make it a little darker. Partially positive. And of course now our benzene can act as the nucleophile. Attack this. We formally break that bond now. And I'm going to come up here to the top. We produce the intermediate. It's analogous to what we were seeing a few minutes ago. So here's a specific example of the intermediate that I illustrated a few minutes ago. Of course, this has lost aromaticity. My charges have to balance. Okay, but first I need to balance my masses. FeBr4 minus. Of course, there are lots of lone pairs around those bromines. So this is a point at which I want to illustrate a fundamental principle for us when we're writing mechanisms. At each individual micro step, so this is a micro step, the formation of the activated complex. This is a micro step. To produce this carbocation intermediate. So at each micro step, first we balance the mass. Second, we balance charge. So let's look at our compound here. We've balanced the mass and the charges. We started out neutral. We eventually get to be neutral. This, of course, is developing partial negative charge over here to balance this partial positive charge if we want to be balanced even with the partial charges. So what do we have left to do here? What's missing or what's extra? We need to lose the proton as we did in the general illustration of this. So here we have the Br lone pair, the bromine lone pair that can act as the base. Pluck off that proton. The two electrons from the carbon-hydrogen bond swing down to reform the pi bond. And now we have formed bromobenzene. Bromobenzene. Of course, the rest of the inorganic part is HFeBr4 there. Okay. So turns out this carbocation, you see, is actually very, very acidic. Right? It's acting as an acid by giving up a proton.